going to start in this idea of learning some definitions. But what I have here is called a reaction diagram. And this is the reaction progress. You'll also hear me call it the reaction coordinate. The key here is at the beginning. This is our reactants. We start off all reactants. Over here will be all products. So you can kind of think of it in terms of time. We go from reactants to products. Now this is potential energy. We'll later be talking about H for enthalpy. So we see all kinds of things going on here. So this is okay, but it's not stressed enough for you to really get a feel for the two ways this graph can look. So I'm going to do that. You know what? I'll just do it right here. Let's get a feel for how that should look. Here's my H, my reaction coordinate. The first one, I'm going to go like that. Here's H of the reactants, H of the products, and it should level up. And you'd be about like that. This is our delta H. The products minus the reactants. Final minus initial. Let's change delta. From here to our hump, E sub A, that's the energy of activation. Every reaction needs energy to get started, even if we get more energy out. This top one, it has this symbol, but it's the transition state. Is the name of it. Transition state is the name of it. Okay. Transition state. It represents someplace in between where if I've got the products splitting up into the reactants splitting up into the products where they're halfway, the bonds are halfway broken. Or maybe I've got things that have collided. And right as they're colliding, and some of the bonds are breaking and the others are making. Okay, so it represents the point. We'll never ever collect the transition state. We can't. Immediately it's going to continue on. All right. So that's one way this looks. The other way is very similar. But on the other hand, opposite. Where's my delta H? So I'm going to start here. And I'm going up to where?
Right there.
To here?
No,
Right in here?
right there.
What do you guys think? So delta H. Oh, this should be really flat. There we go. Goes from our reactants to our products, right? The difference there between these numbers. So here to here. Here's my delta H. Now, without looking about and worry about numbers, remember this number goes up. If I do this, is this bigger or smaller than this? Smaller. So if I do that minus this, am I going to get a positive or a negative? Negative So this has a negative delta H. It's kind of going downhill overall, right? I don't know why I capitalized the H because I've been doing it for the rest of them. Couldn't tell me once that was a sign of insanity, but we voted and we're not crazy. All right. What about this delta H? It's positive. It's going which way? Uphill. All right. This one is exothermic.
That's what I was thinking about. It looks just like the exothermic.
It is. And this one would be endothermic.
I never can remember before.
So the one that goes downhill, we release energy from the bonds after getting some initial energy to get started. That one, we're going to trap energy in the bonds, and not all of it goes into there. Some of it is required to get that process started. Okay. The higher this energy of activation, the slower the reaction goes. The higher that energy of activation, the slower the reaction will go. The easiest way is to think if you're a big fat ant walking along that line. You got a big hill to climb. Even if you're going to get further downhill, it's going to take you longer to get up that hill. Okay. Exothermic, endothermic, transition states, man, oh man. Terrible looking stuff. So what happens at this transition state is it requires things to hit each other. For some things they're more complicated. So we will be looking at those. But the first thing I want to do is to figure out a way of lowering end up at the same place. That energy of activation. What effect would that do?
It would make the reaction go fast.
It would make the reaction go faster. If I provided some other way of doing this reaction with a lower energy of activation, it would make the reaction go faster. That is a catalyst. So a catalyst speeds up the reaction. By lowering
Is there an opposite of a catalyst?
Yes, good question. Inhibitor. It raises the energy of activation, makes it go slow.
Makes sense.
Okay. Now, the way I think about it is this lowering, if I'm doing my big fat ant, it's like going around the hill instead of going over the hill. Right? You're still going to get, even if you go around part of this, the peak of the hill, you're still going to get to the same place in the valley then. It's just faster. All right. The key to a catalyst, it is not a reactant. It is not a product. It has one role in the reaction. What is its role? Speed up the reaction. It doesn't get used up. We'll have exactly the same amount at the end as what we had at the